Hi everyone, today we'll be discussing first order circuits and the response of circuits to changes in voltages. We'll be going over RC and LC circuits and the reaction that they will have to switch sources. Obviously when we're dealing with only a circuit that consists of a resistor and a capacitor, or an inductor and an inductor and a resistor, then we're dealing with first order circuits. We will consider three special functions: the unit step, the unit impulse, and the unit ramp function. And we will see what the response of the circuit is to these functions. And we will also look at the source-free circuits and the switch sources to try to determine what the currents and voltages within the circuit will be. So a first order circuit is characterized by first order differential equations. There are two types of first order circuits. There is the resistive capacitive, which is called an RC circuit, and the resistive inductive, which is an RL circuit. There are also two ways to excite the circuits. One is to have initial conditions, and the other scenario is to basically have independent sources be connected to the circuit. So let's look at the simple scenario where we have a resistor and a capacitor connected in series with one another. This is the scenario where we have a DC source that was connected, but we disconnect the DC source. And so now there's stored energy within the capacitor that will dissipate through the resistor. And we would like to determine what are the relationships between ICE and V, and what equations dictate their relationship. So if we look at the voltage across the capacitor, which is, obviously, if we go back, we'll notice that this voltage is equal to the voltage across the resistor. The voltage across the capacitor is declining with time. We expect that, right? Because the potential is being dissipated through the resistor. This follows an exponential relationship when we show in class what that relationship is, but basically the relationship is given by the initial voltage times e to the power of negative t divided by tau, where tau is referred to as a time constant. This time constant is, for an RC circuit, is equal to, tau is equal to R times C, so resistance times capacitance. This is referred to as the natural response of the circuit because it's the response of the circuit without any sort of outside source. So it's the natural response of the circuit. It's no outside source, and we are seeing the voltage decline using that exponential function. And as I said, we will show why it's exponential in class. Now, the speed at which the voltage decays is dependent on that constant RC, but when we arrive at the point that it's 1 over E, then we say that, okay, the voltage has dropped by one time constant. And so that's basically a metric that we use. And so generally speaking, that exponential dictates that when it's e to the power of -1, then we have reached a one-time constant point. Obviously, different time constants result in different decay profiles, and the larger the time constant, the slower the decay; the smaller the time constant, the faster the decay. So if we know the voltage, we can find the current, and so if we have the voltage here, we can try to find the current by using Ohm's law. The power that is dissipated is given obviously by V times I, which is V naught squared divided by R times it's I squared divided by R, because we don't know what V is. So it's I squared, which is V naught squared, e to the power minus 2t divided by tau divided by R. And then if you integrate this with respect to time, you will arrive at this expression for the total energy that is dissipated. So the key with working with these is that start with an initial voltage across the capacitor at the time constant. with these two items, the voltage as a function of time can be determined, and then you can use the voltage to find the current. And the resistance of the circuit is often determined by finding the Thevenin equivalence. So basically what you will do is you will turn off the sources and the capacitances, and then you will be able to find the Thevenin resistance, and at that point you will replace the circuit with its Thevenin equivalence and the capacitor in series with it, and then you can solve the circuits. We'll solve more problems in class. Thank you very much.